Hello, my name is William.
My name is Jin Choi. And my name is Nathaniel.
So our objective for this thing is we had 5 particular tanks. Three of them were on site. The first tank was the rail car, it brings the fluid. The second tank is a 15,000 gallon storage tank which collects all the fluid. The third tank is a 1,000 gallon smaller tank that is the working fluid for that particular time frame. The third one is a 6,000 gallon tank which is the old dirty fluid, and it would hold it for a couple times. Hold it until we had the tractor trailer come by and empty that tank. So we had the economic considerations for our project were we wanted the shortest pipe runs, we wanted the least amount of fittings, the smallest pipe diameter. We used gravity to eliminate a pump necessary to empty tank 2. We used economic/common building materials for all our tanks and fittings and pipes. We limited gross oversizing and factor of safety. We used 3-phase 480 volt for the motors. We designed for a 3-hour transfer fluid time between tanks. So as you can see right here, here's our front view and side view of our system. In red is the portion where the piping goes. As you can see, it is straight, short distances with a minimum amount of elbows.
Oh, and if you go back, this is the shortest route right here on the side view.
Right.
Shortest pipe.
So shown right here is our the specifications of the pipes we chose. So right here is the pipe velocity for the flow rate that we want. So that shows what size pipe we actually need, and then we oversize just a little bit to a normal size. So 1.86 inches goes to 2 inches, 0.96 goes to 1 inch, so on. Right here we have, like I said earlier, the flow rate that we would need to get those different size tanks to empty, and here's the times that we selected. So you have the different gallons per minute. Over here is the selected pipe tank thickness. So we used the size of the tanks and the density of the fluid to determine the minimum wall thickness. And this minimum wall thickness is with a factor of safety of 2, and obviously all these sizes are not standard sizes. So we upscaled it to 1/8 of an inch as a standard size. Here you can see, like I said earlier, we call for 3-phase 480 power. Now also I have shown here is 3-phase 280 or 208 volts. But as you can see with the 3-phase, the amperage draw is less than half. And with a lower amperage draw, you can use smaller diameter wires, which are cheaper, and also with to go with that is because you have smaller diameter wires, you have less of a voltage loss, or you can get away with less voltage loss because higher voltage, which saves money in cost of electricity and saves money in wiring, which is really expensive. Here we show we have our pump selection. So here are the 3 pumps we chose. The first one is 1475 RPM, and the second 2 are 1775 working RPM. And you have the different type sizes, like this one has a 7.5 inch impeller, this one has a 14 inch impeller, but a really small 1 inch inlet. And that shows because we have a really high head situation going from the first tank to the second tank. So it's going uphill and it's traveling around 600 feet. And the second one is just a normal pump going to 1775 RPM, and it has a normal impeller, and it's not going very far, it's transferring fluid quickly.
From tank 2 to tank 3, there is no pump because we're taking advantage of the gravitational forces there.
Right.
So design considerations, so a couple of things that we're going to note is that we do place the valve before and after pumps and tanks for easy servicing, and we'll show that in a minute. Place the barrier around the tanks to capture fluid from potential tank ruptures, and we design for potential water hammer in mind. So here in a couple of these drawings, we showed some valves and the pump's location in front of the tanks. This one in particular that has 2 valves where we can control the amount of flow going through the pump as well as going after. For the transfer fluid time specifications, you can see the transfer time we listed here. It does regard with the actual flow rate and how much is going through. For the pumps, for selection of the pumps, after we selected the pumps, we led to finding the operating point, and after we found the operating point, it led to us to find its characteristics and determine weight, which is also critical information for our civil engineers colleagues. Now for the potential water hammer, we kept in mind that in order to determine if any system or a particular one system has any water hammer, we had to calculate the expanding wall thickness and compare that to the pipe wall thickness. This over here, the bulge part is actually the calculated wall thickness, and over here is the normal pipe wall thickness that we're comparing to.
For the factors of safety, we designed a factor of safety with number 2. And if there was no size that was that 2, we ended up using the minimum standard size that was at least 2. For the minimum fittings, as Will mentioned, we try to eliminate as much fittings as possible. The most fittings that we used is the coupling 1 inch, which is about 61 couplings. These 1 inch goes to the rooftop to the tank 2, so the pipe used the most in that area, so that's why we have the most fittings there. For the pipe and the miscellaneous materials, we use hangers, Durablock, and pipe supports to have a support for the pipe. And for the pipe length, it's about 670 feet for the combining of 1 inch and 1.5 inch and 2 inch diameter of the pipes. Here's an isometric overview of our project. For the conclusion, we try to use most economic friendly, and the budget wise we
Real world
the combination, and for the budget we use the list fittings, and just by eliminating one pump from tank 2 to tank 3, it was a crucial part to save the budget. For the project duration, we estimated about 8 months at least, and the whole project is sponsored by ODU.